The greatest advantage of deep space is not that it is empty. It is that emptiness cannot steal your heat. Voyager 2 has spent nearly half a century drifting through temperatures only a few degrees above absolute zero, yet the spacecraft is still warm enough to think, measure, and speak. That sounds impossible until you realize something our everyday experience hides from us. Cold does not flow into an object. Heat must find a way out. And in a universe with almost nothing to carry it away, that journey becomes astonishingly slow. Tonight, we trace that journey, discover the tiny source that still keeps Voyager alive, and uncover the one number mission controllers have watched for decades because it quietly determines when the spacecraft will finally fall silent. The warmth in your body is motion. Every molecule in your hand is trembling, jostling against its neighbors, and the faster that trembling, the warmer the thing. Heat is not a substance that fills you up like water in a cup. It is the speed of countless tiny movements, and what we call temperature is really just the average of all that motion. So when your hand feels cold against a railing, nothing cold has actually entered it. The opposite has happened. The motion has left, handed off to something else, and your molecules have slowed down. Cold, in that sense, is not a thing at all. It is the absence of that borrowed motion, the quiet left behind after the warmth has gone somewhere colder. This one is easy to say and hard to feel, because our whole lives teach us to experience cold as something that arrives, an intruder at the door, when really it is only our own warmth leaving. And there is even a floor to how far it can leave. If you slow the molecules down further and further, draining more and more of their motion, you reach a point where they have almost none left to give. We call that absolute zero, and it sits at about minus 460 degrees Fahrenheit. Nothing in the universe has ever quite touched it, but the empty space Voyager 2 moves through hovers only a few degrees above that floor, which is another way of saying the motion out there has very nearly run out. So the real question, the one that decides whether the machine stays warm or freezes, is how that motion gets away from a thing in the first place. And there are only 3 ways it ever can. 3 doors heat can leave through, and every case of something cooling down, anywhere in the cosmos, comes back to one of them or to some blend of the 3. The first is the one you feel the instant you grip that cold railing. We call it conduction. And at the smallest scale, it is almost embarrassingly simple. Your warm, fast-moving molecules collide directly with the slower molecules of the metal. Each collision hands off a little motion, the way a rolling ball passes its speed to a still ball it strikes head-on. The fast ones slow, the slow ones quicken, and heat creeps through the material one bump at a time, the simple result of particles sharing their motion until both sides settle at the same average pace. It is why a metal railing feels so much colder than a wooden bench sitting right next to it in the same winter air. Both are the same temperature, but metal is crowded with loose electrons that shuttle motion through it almost instantly, so it pulls the warmth from your hand fast and keeps pulling. Wood passes that motion along clumsily, so your skin barely registers the loss. The temperature was identical. What differed was only how quickly each one could carry your warmth away. Now notice what conduction always needs. It needs things touching. Molecule against molecule, surface against surface. One crowd of particles pressed up against another. Take away the contact, and this first door quietly closes. The second way heat travels is grander, and you have watched it your whole life without naming it. When you heat a pot of water on the stove, the warm water at the bottom expands, grows a little lighter, and floats upward, while cooler water sinks down to take its place. That slow churning wheel, warm rising and cool falling, is convection. It moves heat not by passing it hand to hand, but by physically carrying the warm material somewhere else and letting the cold flood in behind it. The warm air rising off a candle, the great currents turning through the oceans, the weather over your head tonight, all of it is convection, heat hitching a ride on a moving fluid. And convection asks for even more than conduction did. It needs a fluid to begin with, a liquid or a gas that can actually flow, and it needs gravity to sort the light warm stuff from the heavy cool stuff so the churning can start. Out where Voyager 2 drifts, there is no air to carry warmth off, no fluid to churn, and next to nothing for gravity to sort. The second door closes too, which leaves the third, and the third is the strange one. Because the first two both needed something to move through, some medium, some material in between, the third needs nothing at all. Every object with any warmth in it is quietly glowing, not always in light your eyes can catch, but glowing all the same, shedding energy outward as electromagnetic waves. The warmth in your skin right now is leaving your body this very second as a faint infrared glow, invisible to you, yet real enough that a night vision camera would paint you bright against a cold, dark room. That glow is radiation. It is the same process by which the sun's heat crosses the enormous emptiness between it and us, a gap so wide that the light itself, moving faster than anything can move, still takes about 8 minutes to reach your face on a summer afternoon. Nothing ferries that heat across. It simply travels the way light travels, and it does not need a single molecule in between. Down here on the ground, all three of these usually work at once, together, without asking permission. The cold railing conducts, the winter wind convects, and every surface radiates the entire time. They gang up on any warm thing they can find, which is why a hot cup of coffee left on your kitchen table gives up its warmth in a matter of minutes rather than days. 3 doors, all standing open, all pulling at once. This is the situation Voyager 2 has been living inside for almost 50 years. 2 of those 3 doors have been sealed shut around it. No air to carry its warmth away by convection. Almost nothing to touch, so almost nothing to drain it by conduction. Only radiation remains. Only that faint, ceaseless glow of energy slipping off its surfaces into the dark, with no medium to help it along and none to hold it back. And that single open door changes everything about how the spacecraft cools and about how long it can possibly stay warm. Because a door that needs no medium, that works perfectly in total emptiness, sounds like it should be the fastest way to lose heat of all. A small, warm body glowing itself straight out into the coldest surroundings we have ever measured, with nothing in the way to slow the leak. You would expect a thing like that to freeze in a single heartbeat. So why hasn't it? A door that needs no help, that works in total emptiness, should be the widest door of all. That is the reasonable guess, and it is wrong. Radiation is the only way heat leaves Voyager 2, and it happens to be the slowest of the 3 by a wide margin. The emptiness that sealed the other 2 doors left the machine standing in front of the narrowest one. To see why, we have to look at what that faint glow actually is, and at the strange rule that governs how fast it pours out. Every object with warmth in it radiates, and the hotter it runs, the more it sheds. You have watched this happen to metal. Heat an iron poker in a fire, and it first turns a dull, sullen red. Push it hotter and the red brightens to orange, then to a fierce yellow, then toward a white so bright it hurts to look at. Nobody painted those colors on. They are the poker itself, glowing with its own heat, and the color is a direct readout of how hot it has become. Hotter metal does not just glow brighter. It glows in shorter, bluer waves of light. That glow is thermal radiation you can see with your own eyes, the same process leaving your skin right now, Only your body is far too cool to reach the temperatures where the glow climbs up into visible light. So it stays down in the infrared, real but invisible. Here is what makes radiation behave so unlike the other two. The amount a thing radiates does not climb steadily with its temperature. It climbs by the fourth power of it. That phrase does more than it looks like it does, so let me lay it out. Take how far above absolute zero an object sits, that coldest possible floor we reached in the last stretch, about minus 460 degrees Fahrenheit. Measure the object's temperature upward from there. Now double that number. The object does not radiate twice as hard. It radiates about 16 times as hard, because the effect multiplies by itself 4 separate times. The temperature doubled, and then that doubling gets compounded again and again and again. A thing running a few times hotter than your body, measured from that floor, is not pouring out a few times more energy. It is pouring out dozens of times more. That is why the poker's glow leaps from invisible to blinding over what feels like a modest change in heat. Now run that same rule backward, because that is the direction Voyager 2 lives in, and something quietly remarkable falls out of it. If radiating scales with the fourth power of temperature going up, then it collapses with the fourth power coming down. A warm object left alone in the cold sheds heat quickly at first, while it is still warm. But every degree it loses makes it radiate more weakly, which slows the loss, which means it cools more gently, which slows the loss again. The object is not falling toward the cold. It is easing toward it, applying its own brake harder and harder the closer it gets. The last stretch of cooling stretches out far longer than the first. A thing that lost half its excess warmth in an hour might take many hours to lose the next half, and far longer still for the half after that. This is already enough to overturn the picture most of us carry. We imagine deep space as a kind of infinite freezer that would suck the warmth out of anything instantly. But a freezer works by conduction and convection, by cold air and cold surfaces pressed against whatever you put inside. Strip those away, and you are left with only the glow, and the glow, at ordinary temperatures, is slow. A cup of coffee loses its heat in minutes on your kitchen table because 3 doors are open at once, and the fast ones do most of the work. Seal the fast ones, leave only radiation. And that same cup would hold its warmth for a strikingly long time. The coldest surroundings imaginable do not change that, and the reason why is the part worth slowing down on. An object in space is not only radiating heat away, it is also being bathed in whatever faint radiation comes back at it from its surroundings. The true rate at which it loses warmth is the difference between the two. What it sends out, set against what it takes in. And the surroundings out where Voyager 2 drifts sit only a few degrees above absolute zero. Put that tiny number through the same fourth power rule, and it all but vanishes. The cold of space sends almost nothing back, but it also does nothing to reach in and pull heat out faster. It simply fails to return what the spacecraft loses. The pace of the cooling is set almost entirely by the temperature of the spacecraft itself, not by the cold around it. Being in the coldest place ever measured does not mean freezing fastest. A warm body radiates according to its own heat, and a cold emptiness that returns nothing is not the same as a cold that actively drains you. The frozen surroundings are almost bystanders. They set the floor the spacecraft will someday drift down to, but they do very little to hurry it there. What decides the speed is the machine's own warmth, glowing itself away by a rule that eases off precisely as things get colder. So the reasonable fear that a small, warm object in that dark would freeze in a single heartbeat turns out to be built on the wrong physics. It assumed the cold would come and take the heat. Out there, nothing comes. The warmth only leaves, and it leaves slowly, and it leaves more slowly with every degree it sheds. A machine dropped cold into that emptiness, with no heat of its own, would still take an astonishingly long time to settle all the way down to the temperature of space. The break alone buys years. But a break only slows a fall. It does not stop it. Radiation may be the narrowest door, and it may narrow further as things cool, yet it never fully closes. Warmth is still leaving Voyager 2 every second of every year, a steady infrared glow bleeding off its surfaces into the dark, and nothing about that faint outflow reverses on its own. Left to the break alone, the machine would still be cooling, still sliding toward the cold, just slowly. Something on board has to be pushing back. Something has to be putting warmth in nearly as fast as the glow carries it out, year after year, with no sunlight to draw on and no way to refuel. So where does a spacecraft, alone in the dark for almost 50 years, find a heat it never stops needing? Voyager 2 carries its own heat, and it makes that heat in a way that has nothing to do with sunlight, nothing to do with burning, nothing to do with any fuel we would recognize from an engine or a stove. It comes from the slow unraveling of the atom itself. Tucked deep in the craft sits a small mass of plutonium. It is a heavy, silvery metal, and it stays faintly warm all on its own, with no fire beneath it and no wire running into it. We could hold a shielded piece and feel the heat rising off it the way it rises off a stone left out in the Sunday. Except no sun ever warmed this. The warmth is coming from inside the atoms themselves, out of their very cores, and it does not switch off. It was warm the day we sealed it up in the 1970s. It is warm right now while you lie here. It will still be giving off heat long after every other system on the craft has fallen quiet. To find where that heat is born, we go down into the nucleus. That is the tiny, impossibly dense knot at the center of every atom, where nearly all of its mass is crushed into almost none of its room. And inside that knot, two great forces are locked in a standoff. The protons packed in there all carry the same positive charge, and like charges shove each other away, hard, at that range. On its own, that repulsion would blow the nucleus apart in an instant. Something stronger holds it shut. We call that something the strong nuclear force, and up close it overpowers the electric shoving with room to spare. It has one catch. Its reach is almost nothing. It grips only the particles right beside it and fades away a little farther out. In a small atom, that is no problem at all. Everything sits close enough for the strong force to win cleanly. But plutonium is a giant as nuclei go, with dozens of protons all pushing against one another across the entire width of it, while the strong force can still only bind each one to its nearest few neighbors. The knot holds. It holds only barely. Picture a crowd crushed so tightly together that the people at the far edges are always on the verge of spilling loose, held in by hands that can only reach the person immediately beside them. That is a heavy nucleus, stable enough to last, strained enough that it cannot last forever. So every so often, a small piece of that crowd works its way free. In plutonium, the piece that leaves is 2 protons and 2 neutrons bound into a single tight bundle. We named it an alpha particle, and it is actually the bare nucleus of a helium atom, the second lightest thing in the universe, cast off from one of the heaviest. For a long time, there was a genuine mystery in how it ever gets out at all. By the plain accounting of energy, the alpha particle trapped inside does not have enough of a push to climb over the wall of force penning it in. Think of a ball resting in the bottom of a bowl without the speed to roll up and over the rim. By every ordinary rule, it should sit there trapped forever. And yet, reliably, it escapes. The resolution became one of the first real triumphs of quantum physics, and it is stranger than the puzzle it solved. At that scale, a particle does not sit at one fixed spot with one fixed amount of energy. It exists as a spread of possibility, a haze of where it might be, and a thin edge of that haze reaches straight through the wall to the outside. Once in a great while, without ever having enough energy to cross the barrier in the ordinary way, The alpha particle simply turns up on the far side and races off. We call it tunneling. It is not a metaphor and not a loophole. It is the honest behavior of matter at the smallest scale, and the entire warmth of Voyager 2 leans on it. This is also why we can never point to a single atom and say when it will let go. Nothing counts down inside it. Nothing wears out or builds toward a snapping point. The escape rides on a chance so faint that for any one atom it might come in the next second or hold off for 10,000 years, with no way to tell the two apart beforehand. What rescues us from all that uncertainty is sheer number. In even a small lump of this metal, there are more atoms than there are grains of sand on every shore on Earth. No single one of them can be predicted. The whole crowd can be, exactly. A steady, dependable fraction lets go each second, and out of countless events that are each pure chance comes a heat we can trust down to the fraction of a watt. When the alpha particle finally breaks loose, it comes out moving fast, carrying away the strain the nucleus had been holding as raw speed. It travels almost no distance. Within a hair's width, it crashes into the surrounding plutonium and jolts to a stop, slamming into the atoms in its path as it halts. That collision is where the heat appears. The motion of the flung particle passes into the trembling of everything it struck, and that trembling of packed particles is the very thing we called heat back at the start. One escape warms almost nothing you could measure. But with so many firing off every second, the countless tiny jolts smear together into a smooth, unbroken warmth we could press our hands against. The speed itself hides something stranger than the escape. Weigh the original nucleus before anything happens. Then weigh what remains afterward. The smaller nucleus and the alpha particle added back together. The second weight comes up a little short. A sliver of mass has gone missing. It was not shaved off or hidden somewhere. It has been converted outright into the energy of motion the alpha carries away. Matter itself was spent to buy that speed. This is the plain meaning of the equivalence Albert Einstein gave us, that mass and energy are two faces of one thing, each able to become the other. Here it is not a line of algebra on a board. It is a warm block of metal in the dark, holding a spacecraft above the temperature where its own fuel would freeze solid. The mass lost in each single decay is almost nothing, far below what any scale could ever register. But for one atom, the energy freed is enormous, and a single ounce of this plutonium holds trillions upon trillions of atoms, a steady handful releasing every instant. Add all those slivers of spent matter together and you get a real, usable flow of warmth, close to half a watt of heat from every gram, held nearly level for decade after decade. In the amount the craft carries, that is enough to stand against the whole cold of interstellar space. There is one more gift folded into the kind of particle plutonium throws off. An alpha is heavy and clumsy and stops almost the moment it starts, burying itself in the first material it meets. A single sheet of paper would halt it. The outer layer of your own skin would halt it. All of its energy dumps right there into the surrounding metal instead of streaming out as piercing radiation, which turns the whole mass into a compact, self-contained little furnace that can sit safely aboard without heavy walls to cage it in. Notice what this heat does not need. No oxygen, so there is no flame to feed and nothing to burn out. No light, so the near total darkness costs it nothing. No warmth borrowed from outside to keep it running. The decay follows a schedule written into the plutonium nucleus itself, and nothing in the surrounding emptiness can hurry it or hold it back. We could set this metal down in the coldest corner of the cosmos, and it would go on making heat at the very same pace, wholly indifferent to where it sits. That indifference is the quality we needed. A source that asks nothing of its surroundings is the only kind we could trust to run alone, for decades, in a place nothing else can reach. So now both halves of the picture stand together. On one side, the faint glow of radiation carrying warmth out into the dark, held back by that fourth power break yet never fully stopping. On the other, This knot of unraveling atoms feeding warmth back in, steady and sealed and needing nothing at all. Year after year, the two have hovered near balance, heat leaving and heat arriving at nearly the same quiet rate. The craft has stayed warm through all of it. The cold can still reach it. The warmth simply keeps being remade out of matter itself, faster than the glow can carry it away. And still, you might feel the catch in it already. Every decay that gives off a little heat also spends a little of the plutonium, for good. The knot of unstable atoms is not bottomless. Each pulse of warmth we just followed is one fewer pulse left to give, and no sunlight out there will ever come to refill the supply. The one thing this source cannot escape is itself. It is running down. So how fast is that small warmth fading, and how much of it is even left tonight? The plutonium does not run down in a straight line, and the shape of that fall matters more than the fact of it. To see the shape, we need one number that every unstable material carries with it, a kind of private tempo for how fast its atoms let go. We call it the half-life. It is the time it takes for half of whatever you started with to have decayed away. For the plutonium aboard Voyager 2, that span is about 88 years. Seal up a fresh block of it, weight a bit less than a human lifetime, and half of those atoms will have transformed and given up their heat. The other half will still be sitting there, unchanged, waiting their turn. The part that catches people is what happens next. After another 88 years, the supply does not empty out. Instead, half of what remained goes, which leaves a quarter of the original. Wait again, and you are down to an eighth, then a 16th, the amount always halving, never quite reaching zero. The heat follows that same curve exactly. Strong at first, then weaker still, fading fastest in the early years, and more gently as time goes on. There is a clean reason the fall takes this shape, and it reaches right down to how a single atom behaves. Each nucleus has a fixed chance of decaying in any given stretch of time, and that chance never changes. A plutonium atom does not age. It does not grow brittle or tired or closer to the edge. An atom sealed up 50 years ago is exactly as likely to let go this year as a freshly made one sitting beside it. The atoms have no memory and no clock, and so, at every moment, the same steady fraction of whatever is left decays. When there is a great deal of plutonium, a great many atoms let go each second, and the heat runs high. As the supply thins, that same fraction produces fewer events, and the warmth eases downward in step with the amount that remains. This is where a familiar picture actually misleads us. We tend to imagine a fuel supply draining like sand through an hourglass, running at a steady pace until the last grain falls and it simply stops. The plutonium does not behave that way at all. It does not drain at a constant rate toward an empty moment. It drains in proportion to how much is still there, so the flow is always slowing, and there is never a final grain, only smaller and smaller amounts stretching out ahead. The one thing the hourglass gets right is the direction. Once the sand has fallen, no one in the world can lift it back up. Once a plutonium nucleus has decayed and shed its heat, nothing we know of can rebuild it. There is no lever to pull, no way to feed the block, no reaction we can run to turn the spent atoms back into fresh ones. The warmth only goes one way. Now put real numbers against that curve, since the curve alone does not tell your body much. When the two Voyagers left Earth, each one's generators produced somewhere around 470 watts of electricity. That is a little less than 5 old-style household light bulbs, the bright glass kind that ran warm to the touch. A modest amount of power to run an entire interplanetary spacecraft on, and it has been shrinking every single year since. The craft loses several watts of electricity annually, and after almost 50 years out there, a large share of that original power is simply gone. What runs the whole machine tonight is a faint remnant of what it launched with, And here the story hides a second decline underneath the first, one that makes the fall steeper than the plutonium alone would explain. The heat from the decay has to be turned into electricity, and that conversion is done by banks of paired materials that generate a current when one side is kept hot and the other cool. Those materials do not last untouched. Under the constant heat and the constant flow of radiation from the plutonium, they slowly degrade, and their ability to turn a given amount of heat into usable current fades over the years. So two clocks are running down at once inside that generator. The plutonium yields a little less heat each year as its atoms thin out, and the converter turns a little less of that heat into power as its materials wear. The electricity available to the spacecraft drops faster than the warmth alone, pinched from both ends. Step back from the numbers and the situation is stark and simple. Voyager 2 is living off an ember that no one can relight. The glow of that ember was set the day it was sealed, and from that day forward it has only dimmed, following a curve written into the nature of the atoms and hurried along by the slow tiring of the parts that use it. Every year there is less heat to make, and less of that heat becomes power, and none of it can ever be renewed. For a long stretch, this was no crisis at all. There was so much warmth to spare that losing a little each year changed nothing that mattered. The margin was wide, and the craft stayed comfortable inside it. But a shrinking supply meeting a fixed need can only stay comfortable for so long. Somewhere along that downward curve sits a line the warmth must not fall beneath. It is not the cold of empty space that marks it, and it is not the failure of any instrument. It is a plain physical temperature, a specific number of degrees, below which something essential to the craft stops working the moment it is crossed. Above that line, the spacecraft lives. Below it, a fluid it depends on turns solid, and solid in a way that can break the very lines meant to carry it. So what is that temperature, and what exactly freezes when the warmth finally runs too thin? The threshold has a name and a number, and both are humble enough that it is easy to underestimate them. Voyager 2 steers itself with small puffs of a liquid propellant called hydrazine, fired through little thrusters to nudge the craft and keep its dish antenna aimed back at us across the dark. That liquid freezes at about 35 degrees Fahrenheit. Not hundreds of degrees below zero, not anywhere near the deep cold of space. It freezes at roughly the temperature of a cold morning you have walked through many times, a touch above the point where water turns to ice. That ordinary little number is one of the hard floors the whole mission rests on. To feel why a few degrees can matter so much, we have to look at what freezing actually is, down at the level of the molecules. In a liquid, the molecules are still moving, still sliding and tumbling past one another, held together loosely but never locked in place. That freedom to flow is the whole reason a liquid can travel through a narrow line and be squeezed out of a nozzle on command. Heat is what keeps that motion alive. As you pull heat away, the molecules slow down, and the faint attractions between them start to win out over their movement. Drop below a certain point, and the motion is no longer enough to resist those pulls. The molecules settle into fixed positions, lock into a rigid repeating pattern, and the liquid becomes a solid. The flowing stops. What could be pushed through a pipe a moment ago is now a stiff plug that goes nowhere. For most materials, that would be the end of the trouble. A frozen plug is useless, but it sits there quietly until you warm it up again. Hydrazine carries a nastier trick, and it is the same trick that bursts the pipes in a house during a hard winter. When most substances freeze, their molecules pack together more tightly than they did as a liquid, so the solid is denser and takes up a little less room. Water famously does the opposite. The way its molecules are shaped forces them, when they lock into ice, into an open and roomy pattern with more empty space between them than the liquid had. So ice takes up more room than the water it came from, and it pushes outward with real force as it forms. Hydrazine shares that same stubborn habit. Freeze it inside a sealed tube and it expands as it hardens, shoving against the walls that contain it with a pressure strong enough to split metal. Picture the water line running into an unheated house in January. The water inside freezes, expands, and cracks the pipe wide open, and the real damage shows up later when everything thaws and the break begins to leak. The very same thing threatens the thin propellant lines threading through Voyager 2. If the hydrazine in them ever freezes, it does not simply pause the steering. It can rupture the lines and valves that carry it, and a rupture out there cannot be repaired. There is no thaw that undoes a split tube 14 billion miles from the nearest hand. A single hard freeze in the wrong place could end the craft's ability to point itself. And a craft that cannot point its antenna at Earth is a craft we can no longer hear. This is what makes the modest little number so heavy. The danger out there was never the deep cold of interstellar space as some abstract enemy. The danger is a specific fluid reaching one specific temperature, close to the freezing point of ordinary water, inside one specific set of narrow tubes. Everything about keeping Voyager 2 alive comes down to holding that liquid, and the lines that carry it, above 35 degrees. Not warm, not comfortable, simply above the point where it would harden and break its own plumbing. And that turns out to be a surprisingly delicate thing to guarantee, because a spacecraft is not a single object at a single temperature. It is a sprawl of tanks and struts and instruments and lines, some closer to the warm heart of the craft, some out on cold extremities far from any heat source. Heat does not spread through it evenly. A line running along an outer boom, exposed on all sides to the dark, loses warmth far faster than a tank tucked deep in the body. So the true problem is not keeping the craft warm on average. It is making sure that not one critical drop of hydrazine, anywhere in that whole cold architecture, ever slips below its freezing point, even as the total warmth on board keeps shrinking year after year. Which raises the question the engineers have been living with for decades. With less heat to spend every year, and a whole cold spacecraft to protect, how do you decide where the warmth goes? And what happens when there is no longer enough of it to keep everything above the line at once? Keeping the craft above that freezing line is not a matter of pouring in more heat. There is no more to pour. The warmth from the plutonium is fixed and slowly shrinking, so the real work is holding on to what little there is and steering it toward the places that cannot be allowed to go cold. Every watt matters, and the whole design of the spacecraft's skin is built to keep those watts from escaping a moment sooner than they must. We already know the only door heat can leave through out there. With no air and almost nothing to touch, warmth can only radiate away as that faint infrared glow. So the way to slow the loss is to fight radiation itself, and the trick for doing that is stranger and simpler than it sounds. Much of Voyager 2 is wrapped in a blanket built from many thin sheets of reflective film, layered one over the next with tiny gaps between them, sometimes 10 or 20 sheets deep. Each sheet is a mirror to infrared light. When the warm inner surface glows, the first sheet catches that glow and throws most of it straight back inward. Whatever slips past is caught by the next sheet and thrown back again, and the next. Heat trying to escape has to be handed outward across sheet after sheet, losing ground at every step. And the more sheets we stack, the less of it ever reaches the cold outside. A single reflective layer helps a little. 20 of them together can cut the radiated loss to a small fraction of what a bare surface would give up. The gaps between the sheets carry their own quiet importance. They are held nearly empty, close to vacuum, so that no air can sit between the layers and ferry heat across by touch. The very emptiness that threatens the craft from outside is put to work inside the blanket, sealing off conduction from one sheet to the next, just as it does everywhere else out there. This is the same principle behind the thin, shiny emergency blankets you have seen wrapped around marathon runners at a finish line. A whisper of reflective film weighing almost nothing, turns back the body's own radiated warmth and holds it close. On the spacecraft, the same idea is stacked many layers deep and tuned to the cold of deep space. Insulation only slows the loss. It cannot make heat, and it cannot decide where the heat goes. For that, the craft leans on two more sources, and the first of them is almost too tidy to believe. Every instrument and computer aboard runs on electricity, and no electrical device is perfectly efficient. Some of the current it draws always ends up as waste heat, warmth shed by the simple friction of pushing charge through wires and circuits. In a laptop, that heat is a nuisance we blow away with a fan. On Voyager, to it is a gift. The warmth leaking out of the running electronics helps hold the surrounding structure above the danger line, so the very act of thinking and listening and reporting home keeps parts of the craft alive. Nothing about that heat is wasted out there. It is folded back into the job of survival. Where the electronics cannot reach, the craft carries dedicated heaters, small elements that turn electricity directly into warmth, placed against the tanks and lines and joints most exposed to the cold. Some critical spots also sit near tiny standalone pellets of the same decaying material that runs the main generators, each one a thumb-sized source of steady heat tucked exactly where it is needed. So the warmth on board comes from three streams braided together: the waste heat of the working electronics, the small electric heaters drawing on the generator's dwindling power, and those little pellets glowing on their own. All of it flows outward through the structure and leaks away through the blankets, and the craft holds its temperature wherever those two rates meet. This is what makes the situation a budget and not a switch. A house has a furnace and a thermostat, and when a room grows cold, you simply ask for more heat. Voyager 2 has no furnace to turn up. It has a fixed and shrinking supply of warmth arriving from those three streams, and a fixed set of demands pulling on it from every cold corner of the craft at once. Holding the whole machine above freezing means the incoming warmth has to be enough to cover every last demand, everywhere, with something to spare. For years, there was plenty to go around. The generators put out far more than the craft strictly needed, and the surplus kept every line and tank comfortably warm without anyone having to choose. The budget balanced itself, with room left over. But that surplus has been thinning the entire time, watt by watt, following the curve we trace through the decaying plutonium and the tiring converters. Sooner or later, a shrinking supply and a stubborn set of demands have to cross. The day comes when the warmth arriving is no longer quite enough to keep every part of the craft above its floor at the same time. When that day arrives, the budget can only balance one way. Something has to be taken off the list. So, when the warmth finally runs short, who decides which part of the spacecraft is allowed to go cold? And how do you make a choice like that from 14 billion miles away? When the warmth finally falls short, there is only one thing left to adjust, not the supply, which is fixed by the decay of the plutonium and shrinking on its own schedule. The only thing the engineers can still move is the list of what gets to stay warm. And the way they buy warmth is stranger than it sounds. They do not make more of it. They make it by taking things away. Every instrument still running, every heater still glowing, every circuit still drawing current is a claim on the same small pool of power. Release one of those claims, and the watts it was using come free for something else. This is the only lever they have left, and for years now it has been the one they pull. To see why turning something off creates warmth somewhere else, we have to follow the power itself. The generator produces a fixed budget of electricity each moment, less every year, and that single budget feeds everything at once. It runs the instruments that gather data. It runs the transmitter that carries the signal home. And it runs the heaters, those plain elements that do nothing but convert electricity into warmth, wire resistance turning current directly into heat, placed against the tanks and lines that cannot be allowed to freeze. Every watt spent listening to the sky or measuring a magnetic field is a watt not available to those heaters. So the contest is not really between one science instrument and another. It is between learning something new and keeping the craft alive to learn anything at all. A camera whose work is done, a detector whose readings have gone flat, each stops being a source of knowledge and becomes instead a reserve of power to be spent on survival. One by one, the things the craft can do are traded away to keep the things the craft must do. Underneath that trade sits a second effect, quieter and easy to overlook, and it comes straight out of the physics we have been building this whole time. When you shut down a working instrument, you save its electricity. You also erase the warmth it was giving off while it ran. No instrument is a perfect user of power. Some of every watt it draws leaks out as waste heat, shed by the ordinary resistance of pushing charge through its circuits, and that stray warmth had been quietly helping to hold its own corner of the craft above the freezing line. Switch the instrument off, and that corner cools on its own, before any other change takes hold. So no shutdown is ever a clean gain. It frees power in one place and pulls heat out of another at the same instant. The saving and the loss are bound together, and the engineers cannot count one without the other. Every choice ripples outward through the whole thermal balance of the spacecraft, and before they commit to any of them, they have to trace where that lost warmth was flowing and what will go cold once it stops. It is less like flipping a switch than like redrawing the entire map of where heat is allowed to travel across the craft. Recently, the choices have cut much closer to the bone. With the surplus all but gone, the teams have started switching off some of the heaters themselves, the very elements whose only job was to keep instruments warm. On its face, that sounds like the one thing you would never do. Those heaters exist precisely to hold delicate hardware above the temperatures it was designed to survive. Turning them off means deliberately letting parts of the craft grow colder than their own builders ever meant them to be. The engineers do it anyway. The alternative is losing the parts that carry no redundancy at all. A heater switched off is a handful of watts handed to the systems that truly cannot be sacrificed, and at the very top of that list sit the propellant lines. Keep those lines from freezing, and the craft can still turn itself, still swing its dish back toward Earth, still be heard. Lose them and everything else the craft can do becomes meaningless, since nothing it measures will ever reach us again. When the warmth will not stretch to cover everything, you protect the ability to steer and to speak, and you let the rest go cold. Slow down on what that decision actually asks of a person, because the physics and the human weight of it are the same fact seen from two sides. These are engineers choosing from 14 billion miles away to strip heat from a machine they will never see again and can never touch. The hardware they are adjusting was built half a century ago by people many of whom have retired or died in the years since the craft left home. And the distance turns every action into an act of patience most of us would find unbearable. A command to shut off a single heater leaves Earth and travels for most of a day before it even arrives, moving at the speed of light the entire way and still taking that long to cross the gap. Then most of another day passes before any confirmation comes back the same slow road. They send the instruction into the dark and wait the better part of 2 days, unable to watch, unable to intervene, to find out whether the part they let go cold quietly took something vital with it as it chilled. There is no fast correction available across that gap. Each trade is made once, carefully, and then simply lived with, whatever it turns out to have cost. What carries them through a choice like that is not nerve. It is a model, a detailed running account of the craft's heat kept on the ground, tracking where every watt of warmth is born and where each one drains away. Before anything is switched off, they run the loss through that model first. They work out how far the affected region should cool once its heat is gone, how quickly it will get there, and whether the new, colder balance still leaves a margin above the freezing point of anything that matters nearby. The model is their only pair of eyes on a spacecraft no telescope can resolve and no camera can show them. It stands in for the machine they cannot reach, letting them rehearse each loss safely on the ground before they ever commit it to the sky. And a model is never more trustworthy than the assumptions built into it. This one rests on decades-old test data, on how each component behaved when engineers deliberately chilled it in a laboratory long ago, on the coldest temperature each part was ever actually measured to endure. Inside that tested range, the model speaks with confidence. Carry a component below the coldest point anyone ever tried on the ground, and the model is no longer describing something known. It is extrapolating past the edge of its own evidence into temperatures the hardware was never checked against. That edge is exactly where the recent heater shutdowns have pushed the craft. Instruments out there are now sitting well below the coldest temperature they were ever tested for, colder than their own makers ever deliberately took them. By the careful logic of the model, several of them should have stopped by now. The safe engineering assumption had always been that hardware taken past its rated cold limit might simply cease to function, its materials contracting, its delicate parts no longer behaving as designed. So the teams made these trades braced for exactly that. They expected that some instrument, chilled beyond every temperature in its record, would fall silent and never come back. That expectation was the reasonable one. It was the responsible one. It was also, as the craft has gone on reporting home from the far side of decision after decision, not what happened. So what does a machine actually do when we take it colder than we ever dared to test, and instead of failing, it keeps working? The first thing to untangle is why cold should threaten a machine at all. Space is not reaching in to smash anything. There is no force out there, no impact, only the slow loss of warmth we have been following the whole way. And yet engineers have always treated deep cold as a real danger to hardware, and they were right to. The threat is quieter than a blow, and it lives inside the materials themselves. Nearly everything shrinks as it cools. Pull heat out of a solid and its atoms tremble less, sit a little closer together, and the whole object draws inward and contracts. On its own, uniform shrinking would cause little trouble. The problem is that a spacecraft is built from many different materials pressed and bonded together, metals and ceramics and plastics and glass, and no two of them shrink by the same amount for the same drop in temperature. A metal contact might pull inward strongly, while the ceramic it is fixed to barely moves at all. As the cold deepens, those mismatched materials drag against one another at every joint where they meet. The strain builds where a wire is soldered to a board, where a seal grips a fitting, where two dissimilar parts were fused together on a workbench half a century ago. Push that strain far enough and something gives. A joint cracks. A bond lets go. A connection that carried a signal for decades opens into a break no one can reach. Cold works a second change on materials, subtler than shrinking. It can make them brittle. Warmth gives the atoms in a solid enough motion to shift and flex a little under stress, to bend rather than snap. Drain that warmth away, and the same material grows stiff and glassy, more likely to fracture cleanly under a load it once would have absorbed. This is the same reason a rubber band pulled from a freezer can shatter instead of stretch, and why steel that holds up fine in summer can crack in extreme cold. In a machine full of tiny wires and thin films and delicate mechanical parts, that shift from flexible to fragile is a genuine hazard. A part chilled far below its design range might survive sitting still and then break the moment it is asked to move or carry current. So the fear behind every one of those heater shutdowns was reasonable and specific. It was not a vague dread of the cold. It was the expectation that somewhere in that aging hardware, some mismatched joint or brittle component pushed past the coldest temperature it had ever been checked against would finally give way and take a vital function down with it. And this is where the gap between what we test and what is true opens up. When a component is qualified for flight, engineers chill it in a laboratory to some rated low temperature and confirm it still works. That rated number is not the point where the part breaks. It is the coldest point anyone bothered to verify, chosen with deliberate caution and a wide margin built in. The true failure point almost always lies somewhere colder, past the last temperature ever tested. Nobody knows exactly where, because nobody ever took the part that far. The rated limit marks the edge of our knowledge, not the edge of the hardware's endurance. For decades, that distinction never mattered. There was warmth to spare, and every part lived comfortably inside its tested range. So the question of where it would actually fail stayed purely theoretical. The heater shutdowns turned that theoretical question into a live one. By switching off the warmth, the engineers pushed instrument after instrument down past its rated floor and out into the untested cold beyond, into the very region the laboratory data had never mapped. They were, in effect, running the experiment nobody had run on the ground, except the laboratory was interstellar space and the sample could never be recovered. And what they found, over and over, was that the hardware kept working. The instruments crossed below their rated limits and went on reporting, colder than their makers had ever deliberately taken them, still faithfully returning data across the long gap home. The margin between tested and true had been wider than anyone dared assume. There is one more piece of physics that makes this less of a miracle than it first appears, and it turns the intuition around entirely. We picture cold as pure enemy to electronics, but for a great deal of electronic hardware, cold is not harmful at all. It is helpful. Inside the semiconductors that do the actual work of computing and sensing, electric current is carried by charges moving through a lattice of atoms. Those atoms are always vibrating with heat, and their vibration is exactly what gets in the way of the moving charges, scattering them, resisting their flow, generating stray heat and electronic noise. Cool the material down and the vibration quiets. The charges move more freely. The resistance drops, the noise falls, and many circuits actually run cleaner and more precisely at low temperature than they do warm. This is why the most sensitive detectors we build, the ones that hunt for the faintest signals, are often deliberately chilled to work at all. For those parts, the cold of deep space is not a threat to be survived. It is close to an ideal operating environment. So the real picture is split in two, and the engineers had to weigh both halves. The cold genuinely endangers the mechanical side of the craft. The joints and seals and moving parts and mismatched bonded materials that crack and stiffen as they shrink. But the electronic heart of many instruments does not mind the cold, and in some ways welcomes it. The great uncertainty in every heater shutdown was never whether the electronics could think in the cold. It was whether the physical body around them, the housing and the connections and the fragile mechanisms, would hold together as it chilled past anything ever tested. That the answer kept coming back, yes, again and again, is the quiet vindication running underneath this whole late chapter of the mission. It would be easy to read that success as proof the craft can endure anything, that the cold has been beaten. That reading would be wrong, and the engineers are the first to say so. Every part still has a true failure point out there in the untested dark, a temperature at which the joints finally crack or the mechanisms finally seize, and each shutdown carries the craft a little nearer to finding it. Surviving colder than expected does not mean surviving forever. It means the floor is lower than the charts showed, not that there is no floor. Somewhere below lies a temperature where the good luck runs out. And beneath the cold pressing in from outside, the deeper clock has never stopped. The plutonium is still thinning, the warmth still fading on its fixed curve, no matter how bravely the hardware takes the chill. Which leaves the question the whole mission now turns on. If the warmth is always shrinking, and the cold keeps proving survivable but not endless, how much time is truly left before there is not enough heat to keep even the most essential part of Voyager 2 alive? The strange thing about asking how long Voyager 2 has left is that half the answer is known with real precision and the other half is barely knowable at all. The warmth itself follows a curve we can draw far into the future. The decay of the plutonium is one of the most predictable processes in nature, steady and blind to everything around it. So we can say with confidence how many watts the generator will produce 5 years from now, or 10, or 20. That part is arithmetic. What we cannot pin down is the moment those falling watts finally cross below what the craft needs to survive, because that crossing depends not on the plutonium alone, but on every uncertain thing we have been circling, on how cold each part can truly go before it fails, on which fragile joint gives first, on margins nobody ever measured. The supply is a clean line sliding downward. The threshold it is falling toward is a blur. We can still see the shape of what is coming, even without a date stamped on it. As the power keeps dropping, the shutdowns that have already begun will continue, and they will follow a clear order of priority. The instruments still gathering data will go first, one after another, each switched off as its share of the power becomes too precious to spend on anything but survival. After the instruments come the heaters that were keeping non-essential systems warm, already being sacrificed now. And somewhere near the very end of that list sit the two things the whole mission finally reduces to: the ability to keep the propellant from freezing so the craft can still turn, and the transmitter, the single radio voice that lets it reach us at all. Everything else is negotiable. Those two are the craft's actual heartbeat, and the last watts will be guarded for them long after every instrument has gone dark. Staying warm, though, is only half of what it takes to still be heard, and the other half hides a second threshold most people never think about. Even with the transmitter powered and the antenna aimed perfectly at Earth, there is a hard physical limit on how faint a signal we can still pull out of the dark. The radio signal leaves Voyager 2 with a strength smaller than the bulb in a refrigerator, only around 20 watts of power poured into the void. That signal spreads outward as it travels, widening into an ever larger sphere, its energy thinning across a surface that grows with the square of the distance, the same way sunlight thins on its way out. By the time that whisper has crossed the gulf back to Earth, the fraction of it landing on even our largest dish is almost unimaginably small, a power measured in tiny slivers of a billionth of a watt. We catch it at all only with enormous antennas many stories across, cooled and tuned to sieve that murmur out from the natural radio noise of the universe itself. It works, but only just, and only because the signal still rises a hair above the noise floor. That noise floor is the second clock. The dimmer the transmitter grows as its power fades, the weaker the signal it can send, and the harder it becomes to lift that signal clear of the background hiss. There comes a point on the curve where the craft could still be perfectly alive, still warm, still turning, still transmitting with all the power it has left, and yet the signal arriving here has simply sunk beneath what any dish on Earth can distinguish from noise. The voice would not stop so much as dissolve, fading down into the static until we could no longer be certain which faint murmur was Voyager and which was the hum of the cosmos behind it. So the end, when it comes, may not be a dramatic failure at all. It may be a slow submersion, the signal thinning year by year, until one day the craft is still speaking and we can no longer tell its whisper from the dark. Put the two thresholds together, and the honest answer to how long it has takes the shape of a window rather than a date. Sometime in the years ahead, not far off, the falling power will force the last instruments dark and leave only the barest engineering signal, a simple tone confirming the craft still lives. For a while after that, even with nothing left to measure, the transmitter may go on sending that faint tone home, and we may go on catching it, until either the warmth slips too low to hold the essential systems, or the signal sinks too far beneath the noise to find. Which of those comes first, and exactly when, no one can say with certainty. The curve gives us the decade. It does not give us the day. What it does tell us plainly is that the direction never reverses. Every projection, however uncertain in its timing, points the same way. Less power next year than this. Fewer systems the year after. A slow, orderly surrender of everything the craft can do, down to the last two things it must. And here is the part that stays with me when I follow this all the way out. Whatever year that final signal fades, the craft does not end when we stop hearing it. It goes silent to us, but it keeps going. The plutonium will still be warm inside it the day the last tone dissolves into static, still decaying, still shedding its faint heat into the aluminum and the wiring long after there is no one listening and nothing left to say. The warmth that kept it alive does not switch off the moment we lose the signal. It simply carries on, unwatched, fading by that same slow curve for years and years beyond the silence. The mission ends when we can no longer hear it. The cooling does not. It goes on out there in the dark, gentle and unhurried, long after the last of us has stopped waiting for a reply. So a quieter question opens underneath the loud one. We keep asking how long until it goes cold, as if cold were a finish line the craft crosses on some particular night. But once the warmth finally runs out, what does going cold actually mean for a thing adrift in the emptiest place there is and missed to? How cold does it truly get out there? And how long does the last of the warmth really take to leave? Follow the craft all the way past the last signal, past the final faint tone dissolving into static, to the distant day when the plutonium has thinned so far that it can no longer hold anything warm. The heat that was remade every second for a century finally stops being remade. And with the inner source gone quiet, Voyager 2 becomes, for the first time in its existence, a purely passive thing. No warmth arriving, only warmth leaving, glowing itself away through that single open door of radiation with nothing left on board to answer it. The question is what it settles toward, and how long the settling takes. The easy answer is that it falls to the temperature of space, and the easy answer hides the most interesting part. Empty space does not actually have a temperature of 0. Even the deepest void between the stars is faintly warm, bathed in a whisper of radiation left over from the birth of the universe itself. That radiation fills all of space, in every direction, a faint background glow cooled over billions of years, down to a little under 3 degrees above absolute zero. In the units we have been using, that is roughly minus 455 degrees Fahrenheit, bitterly, unimaginably cold, and yet not nothing. It is a real floor of warmth, the same few degrees everywhere we have ever looked, and it is the temperature the craft is truly falling toward. Not 0. That gentle leftover heat of creation, soaked into every cubic inch of the dark. So Voyager 2 does not cool forever downward into some bottomless chill. It cools until it matches that background, until the warmth it radiates away is balanced by the faint warmth the background radiates back. At that point, it stops losing heat on the whole, because it is giving and receiving in equal measure, resting at last in step with the coldest steady temperature the universe has to offer. But reaching that resting point is not quick, and the reason reaches right back to the physics we started with. As the craft cools, the same fourth power rule that governed it from the beginning tightens its grip. Every degree the metal loses makes it radiate more weakly, which slows the loss, which means the next degree leaves even more reluctantly than the last. The cooling does not glide smoothly down to the floor. It races at first, while the craft is still warm, then crawls, then barely moves at all, easing toward that final temperature along a curve that flattens without ever quite lying down. The last sliver of excess warmth takes longer to shed than all the warmth before it combined. And here the physics turns genuinely strange. We tend to imagine absolute 0 as a place a thing could arrive at if only it got cold enough, the temperature where all motion stops and every atom falls perfectly still. Nature does not allow the arrival. There is a law, worn smooth by more than a century of testing, that says you can approach absolute 0 but never actually touch it. Each step closer costs more than the step before. Pulling the last trace of motion out of matter would take an endless number of ever harder stages, and the endlessness is the point. The floor exists, and it can be neared without limit, and it can never be stood upon. A thing cooling in the dark is always closing the gap and never closing it fully, forever a hair above the stillness it is falling toward. Even if the craft could somehow shed every scrap of ordinary heat, something would still be moving inside it. Down at the smallest scale, the rules that govern atoms forbid them from ever going perfectly still, keeping the faintest tremor of motion alive even at the coldest temperature allowed. Absolute zero, the true and total stillness we picture, is not a place matter can be. It is a limit matter leans against, closer and closer, across spans of time that dwarf everything else in this story. So the honest shape of the craft's cooling is not a fall to a stop. It is an endless, ever gentler approach, forever nearing the leftover warmth of the universe and never fully arriving, its temperature sliding down a curve that has no last point on it. There is one more turn, and it lifts the whole picture up to the largest scale we have touched yet. That background warmth the craft is settling toward is not fixed either. The universe is expanding, stretching outward in every direction, and as it stretches, the ancient radiation filling it stretches with it and cools, degree by tiny degree, over billions upon billions of years. The floor itself is sinking. Across time spans long enough for galaxies to drift apart, the background will slip nearer and nearer to the absolute zero it can never reach, and the resting temperature of anything adrift in the void will follow it down, chasing a floor that keeps receding just ahead. Voyager 2, cold and silent and long forgotten, would drift through that deepening chill, cooling in step with a universe that is itself slowly running toward the stillness none of it can ever quite achieve. So the word we started with, frozen, turns out to name something far gentler and far stranger than a moment of ice. There is no night when the craft suddenly goes cold, no instant of freezing over. There is only a slow leaving of warmth that grows slower the longer it goes, a temperature easing down across ages toward a floor that itself keeps sinking, an approach with no arrival written anywhere in it. The machine does not freeze so much as it very slowly, very quietly, joins the temperature of everything around it, and then keeps pace with that cold, as the cold itself deepens over the life of the universe. Not an ending, a settling, the most patient process there is. And running underneath all of it, from the warm generator of today to that unreachable stillness 10 billion years from now, is a single direction that never once reverses. The heat always leaves. It never gathers back. Every step of this long cooling, from the first watt lost to the last tremor of motion, moves one way and only one way, and nothing anywhere in the craft or the space around it ever nudges it backward. That one-way flow is so constant we have stopped noticing it, and yet it may be the deepest thing in the entire story. So why does heat only ever move in that single direction? And what does that unbroken one-way drift have to do with the way we feel time itself passing, here, tonight? We have watched heat leave Voyager 2 in 100 forms by now, and every single time it moved the same way. Out of the warm plutonium and into the cooler metal. Out of the warm metal and into the colder space. Never once the other way. No one ever had to enforce that. The heat was never pushed downhill by some hand making sure it obeyed. It simply went on its own, every time, from the warmer thing to the cooler one. And it has done so in every experiment anyone has ever run anywhere without a single exception. That perfect one-way habit has a name. We call it the second law of thermodynamics, and it may be the most unbreakable rule we know. The strange part is that nothing in the small-scale rules requires it. Zoom all the way down to two molecules colliding, one fast and one slow, and watch them trade motion. The fast one slows, the slow one speeds up. Now imagine filming that collision and playing the film backward. The reversed version breaks no law at all. It looks like a perfectly ordinary collision, one that could happen just as easily forward or back. Every basic interaction between particles works equally well in both directions of time. There is nothing in the physics of a single bump that prefers before to after. And yet step back up to the world we live in, the world of warm cups and cooling spacecraft, and the direction is suddenly absolute. Heat spreads out and never gathers back. Where does a one-way street come from, when every brick in it was laid by a rule that runs both ways? The answer is not a force. It is a matter of counting, and it is one of the deepest ideas in all of physics. Picture the heat in the warm plutonium as energy shared among an unthinkable number of trembling atoms. There are countless different ways that energy could be arranged among them, countless patterns of which atom holds how much motion at any instant. Now ask a simple question. Of all those possible arrangements, how many have the energy bunched up, concentrated in one small warm region with cold all around it? And how many have it spread out evenly, shared smoothly across everything? The spread out arrangements outnumber the bunched up ones so overwhelmingly that the comparison stops meaning anything. For every way to keep the heat concentrated, there are more ways to spread it than there are atoms in the craft, multiplied by itself many times over. So when the atoms jostle and trade energy at random, they are not being pushed toward evenness. They simply stumble into it, because almost every arrangement they could possibly land in is one where the heat is more spread out than before. Concentrated heat is rare. Spread heat is common. Random shuffling walks from the rare toward the common, every time, for no reason other than sheer overwhelming odds. That measure of how spread out the energy is, how many arrangements match what we see, is what we call entropy. A warm object in a cold room is a low entropy situation, energy penned in a small space, one of the rare arrangements. As the heat leaks out and evens itself across the room, the entropy climbs toward the common spread out state. The second law, underneath its stern name, is really just the statement that the likely thing happens. Systems drift from rare arrangements toward common ones, from concentrated toward spread, from order toward the vast disorder that surrounds it on all sides. Heat flows from hot to cold, not because it must, but because the reverse is so staggeringly unlikely that in all the history of the universe, it has effectively never been seen. It is not forbidden for a cold room to gather its warmth back into one hot spot. It is merely so improbable that you could wait far longer than the age of the cosmos and never catch it happening once. Here is the turn that lifts this out of physics and into something you feel every waking moment. This one-way spreading is the only process in nature with a built-in direction, and so it is the thing that gives time itself a direction. Think about how you know which way time runs. A cup falls and shatters, and it never leaps back together. Warmth drains from your coffee and never floods back in. Smoke drifts apart and never regathers into the flame. Every one of those is entropy climbing, heat and matter spreading from the rare into the common, and every one runs only forward. The difference between the past and the future, the whole felt sense that time moves and does not come back, traces to this single fact about energy fanning out. The past is simply the direction where things were more concentrated, more ordered. The future is the direction where they have spread. We call the spreading the flow of time, and physics has found nothing else that separates one direction of time from the other. Which means the slow cooling of Voyager 2 is not some sad exception to a warm universe. It is the universe doing the one thing it always does, told in a single small machine. The heat gathered in that plutonium, rare and concentrated, is fanning out into the enormous cold around it, climbing toward the spread-out state that almost everything eventually reaches. The craft is not fighting time when it cools. It is keeping perfect step with it. Its warmth draining into the dark is the same motion as the shattering cup and the cooling coffee and the drifting smoke, the same one-way slide from concentrated to spread that we experience from the inside as the passing of the hours. To watch it cool is to watch time itself, made visible in a slow loss of heat 14 billion miles away. And the deepest question hiding in all of this is one we still cannot fully answer, so let me be honest about where the certainty ends. If systems always climb from rare arrangements toward common ones, then the universe must have begun in an extraordinarily rare, extraordinarily concentrated, low entropy state, or there would be no downhill for anything to run. Why it started so ordered, so far from the spread-out sprawl it has been drifting toward ever since, is a question that reaches past anything settled. We know the direction things flow. We can count the arrangements and see why. What we do not fully know is why there was ever a slope to begin with, why the cosmos opened in a state rare enough to give heat somewhere to go and time a way to move. That slope is the reason your coffee cools, the reason the craft grows cold, the reason tonight will not run backward into this morning. And underneath all the physics, it is the reason there is a tonight at all. So what does it mean that you, lying here, are made of the very same one-way flow, your own warmth spreading gently into the room as you begin to let the day go? Everything we have followed out there is happening, right now, in you. You are a warm object in a cooler world, and you are losing heat exactly the way the spacecraft does, by the same rules, through the same open doors. Your body holds itself near 99 degrees Fahrenheit, and the room around you is cooler than that. So warmth is flowing out of you this very moment and into the air and the sheets and the space you lie in. Some of it leaves by touch, carried off wherever your skin meets something cooler. Some rides away on the faint currents of air your body warms and sets gently rising. And some of it simply glows off you as infrared light, that same invisible radiation streaming off the craft, pouring off your skin into the dark of the room whether you feel it leaving or not. You are giving off more of it than you might guess. A resting human body sheds heat at something close to 100 watts, near enough to the old bright bulb we measured the spacecraft against at the very start. Lie still in a quiet room and you are quietly warming it, radiating roughly as much heat as a reading lamp, hour after hour, without a single thought given to the effort. That warmth is real energy, and it is always leaving, always draining into the cooler world around you, never once flowing back in on its own. By the plain physics of it, you should cool just as surely as the coffee and the craft, and yet your temperature holds, steady and warm, night after night, year after year. Something in you is answering the loss. You already know what it must be, because we traced the same logic through the plutonium. If the warmth keeps leaving and the temperature holds, then the warmth must be getting remade at nearly the rate it escapes. Your source is not a decaying metal. It is the food you ate today. Deep inside your cells, the energy locked in that food is being released in a slow, controlled way, broken down through long chains of chemistry that free its stored energy a little at a time. A small part of that released energy runs the work of being alive, the pumping and thinking and moving. The larger part comes off as heat, the warmth of countless tiny reactions running in every cell at once. You are burning your food in the gentlest possible fire, and the warmth of that fire is what holds you above the temperature of the room. Cut off the fuel, and you would cool. As long as it keeps coming, you keep making the heat as fast as the world carries it away. This is where the deepest law we touched reaches all the way into your body, and it says something startling about what you are. A living thing is a pocket of order, a place where matter is arranged with astonishing care, held far from the spread-out sameness that the second law pulls everything toward. By rights, that order should be decaying, unraveling toward the disorder all around it. You hold it off by a constant trade. You take in ordered energy from your food, Use it to keep your own structure intact, and pour the leftover out into the world as heat and waste, as disorder shed into your surroundings. You are not breaking the second law by staying ordered. You are riding it. You keep yourself concentrated and low in entropy by raising the entropy of everything around you a little more, warming your room, spreading your heat, exporting disorder so that you can stay ordered inside. Life does not defeat the drift towards spread-out sameness. It borrows against it, staying an island of order by feeding the ocean of disorder that surrounds it. The blanket over you plays its own quiet part in this, and it works on a principle we have already met, turned to a gentler purpose. Out on the spacecraft, warmth could only leave by radiation, so its blankets are mirrors, built to throw that infrared glow back inward. Your blanket faces a different loss. Around you there is air, and that air is the main thief, carrying your warmth off by touch and by the slow currents it stirs. So your blanket does not mirror. It traps. It holds a layer of still air close against your skin, a pocket of warmth that cannot circulate and cannot carry your heat away, sealing off the very paths of loss the vacuum had already sealed for the craft. Both are the same act underneath, slowing the escape of warmth, keeping the heat near its source a little longer. The craft fights radiation with mirrors because that is its only leak. You fight moving air with a trapped still layer because that is yours. Two answers to the same ancient problem of holding on to warmth in a world that keeps pulling it away. Then there is what happens as you begin to fall asleep, and it is not a pause in any of this. It is a shift in the settings. As sleep comes on, your body eases its own temperature down, letting the core cool by a fraction of a degree, dialing the inner fire a little lower for the night. The drop is small, less than a single degree, and it is part of how sleep arrives at all. Your warmth sinks slightly, your heat output softens, and the cooling itself is woven into the signal that tells your body the day is done. This is why a cool room helps you sleep, and an overwarm one fights you. You are trying to shed a little heat to let your temperature drift gently downward, and a room that lets that warmth leave makes the sinking easier. The same slow loss of heat we have watched carry a spacecraft toward the cold is, in you tonight, the quiet mechanism of rest. You cool a little on purpose, and in the cooling you let go. So the machine drifting 14 billion miles from here, and the body lying still under a blanket, are running the very same physics, told at wildly different scales. A warm thing in a cold surrounding, losing heat it cannot help but lose, remaking that heat from a source that will not last forever, holding its temperature in a balance between the two. The craft remakes its warmth from unraveling atoms and will hold that balance for a few more decades. You remake yours from a single day's food and must renew the source again tomorrow and the day after, for as long as the fire keeps being fed. The difference is only in how long the source lasts and where it comes from. The law underneath is one and the same, from the plutonium to the plate, from the far edge of the solar system to the warmth held close beneath your blanket right now. And if the same slow loss of heat runs through both, then the same one-way flow of time runs through both as well. So what does it mean that the warmth leaving your body tonight is moving in exactly the same direction and by exactly the same law, as a probe cooling in the dark long after everyone who built it is gone? The same one-way flow that cools your body tonight will still be at work on the craft 10,000 years from now, and 100,000, and far beyond that. So follow it out past every human timescale and ask a plain question. Once Voyager 2 has gone cold and silent, once no one is listening and nothing is left to say, how long does the machine itself last as a physical object drifting through the dark? The heat is one clock. The body of the craft is another, running far slower, and it keeps ticking for a span that makes the mission itself look like a single breath. Start with where it is going, because motion out there behaves unlike anything our intuition trained us for. Voyager 2 has already passed beyond the sun's outermost influence, and nothing ahead of it will slow it down. There is no air to drag on it, no surface to run into, almost nothing at all to touch. A thing set moving in that emptiness simply keeps moving, holding its speed for as long as nothing acts on it, and out there almost nothing ever does. The craft is coasting at tens of thousands of miles per hour, and will keep coasting at very nearly that same speed for millions of years, carried forward by nothing but the push it was given long ago, and the deep stillness of a space with nothing in it to stop the drift. It is not headed for any star in particular. It is falling in a long, slow loop around the whole galaxy, taking a couple of 100 million years to circle the Milky Way's center once, the same enormous orbit our sun and every star around us is riding. So the craft is not really leaving the galaxy. It is joining the traffic of it, one more small body orbiting among the stars, and the question becomes what wears on a thing across those spans. Out there, the erosion is patient, almost past imagining. Space between the stars is not perfectly empty. It holds a thin haze of dust and gas, unbelievably sparse, thinner than the best vacuum we can make on Earth, but the craft is moving through it fast and for a very long time. Grain by grain, atom by atom, that faint drizzle sandblasts the outer surfaces, etching them so slowly that in 1,000 years the change would be almost nothing, yet over millions of years, it steadily wears the exposed metal down. Alongside the dust comes a constant sleet of cosmic rays, bare atomic nuclei flung out by distant exploded stars, moving so close to the speed of light that they drive deep into whatever they strike. Each one knocks a few atoms loose from their places in the metal, and across the long ages those countless tiny impacts slowly break down the ordered structure of every solid surface. The craft turns to the dark. Set against that slow erosion is the sheer stubbornness of solid matter in the cold. Chemistry, the reshuffling of atoms into new arrangements, needs warmth, and it needs something to react with. Out in that deep cold, with the craft frozen near the temperature of the background sky and almost nothing around it to react against, the ordinary decay we know on Earth nearly stops. Nothing rusts, because there is no oxygen to do the rusting. Nothing rots, because there is nothing alive. The gold record bolted to its side, the aluminum frame, the traces of the plutonium still faintly warm inside, all of it sits in a stillness so complete that the usual agents of ruin have almost no purchase. The craft is being erased, but only by the faint sandblasting of dust and the slow gnawing of cosmic rays. And against those alone, a solid machine can endure for a span that beggars the imagination. Best estimates give the body of Voyager 2, recognizable as a made thing, a life measured not in thousands or millions of years but in hundreds of millions, perhaps longer than the Earth that built it, will remain intact. Push the timescale further still, and we reach the edge of what physics can honestly claim. Over long enough spans, the erosion keeps going. The plutonium, following the same decay curve we traced, transforms nearly completely, its warmth long gone, its atoms settled into stable lead. The surfaces wear thinner. The record slowly loses its finest grooves to the endless faint bombardment. And out past all of that lie questions where the science genuinely thins into open debate. Whether the very particles the craft is built from, the protons at the heart of every atom, are themselves perfectly stable across cosmic time, or whether they too dissolve over spans so vast they dwarf the present age of the universe many times over, is something we have looked hard for and not yet settled. We have watched enormous quantities of matter for signs of a proton coming apart and have never once caught it happening, which tells us that if it happens at all, it is staggeringly rare. Past a certain horizon, the honest answer is that we do not fully know what becomes of matter left alone long enough, and the craft's ultimate fate dissolves into that uncertainty along with everything else. What we can say plainly is the part that matters for tonight. Long after the last signal fades, Long after the warmth we have followed this whole way has drained down to the temperature of the sky, the craft goes on. It keeps its speed. It keeps its shape for ages. It carries its small frozen cargo of metal and memory in a slow orbit around the galaxy, worn at by nothing more violent than starlight and thin dust, enduring in the cold precisely because the cold has stilled almost everything that could destroy it. The same emptiness that let its warmth escape so slowly also lets its body last so long. The vacuum that was its quiet threat is also, across deep time, its preservation. It kills the warmth gently and guards the frame faithfully, both by the very same absence of everything. A thing can go cold and still endure. The warmth leaving is not the same as the object ending. The craft will drift on, quiet and preserved, for 100 million years of orbits after its last degree of heat is gone, a made thing outlasting its makers and its whole warm origin by spans none of us can feel. So if losing its warmth is not the same as its ending, then what, in the end, was the warmth ever really for? What did all that careful heat actually buy across the few decades it lasted? The warmth bought one thing above everything else. The warmth bought knowledge. For as long as the heat held the instruments above their failing point, the craft could sense the place it was moving through and turn what it sensed into a signal we could read back home. Every degree of warmth kept alive out there was spent, in the end, on the single act of finding something out. That trait is stranger than it sounds, because knowledge is not the weightless, airy thing we usually take it to be. It carries a real physical cost, paid in energy and paid in heat, and the craft paid it without pause the whole time it worked. To record a single fact about the world, the craft has to change something inside itself. A measurement is not an idea floating free. It is a physical mark, a switch flipped, a charge moved, a pattern set into memory that stands for the thing being measured. When an instrument registers the strength of a magnetic field or the count of particles streaming past, it must arrange a piece of matter inside the craft into a specific, ordered state that faithfully mirrors the world outside. And arranging matter into a particular ordered state out of the many states it could have been in always takes energy. Nothing gets recorded for free. Every bit of information the craft ever captured began as a small, deliberate ordering of matter, and that ordering had to be powered by the warmth on board. This links straight back to the deepest rule we followed, the one about spreading and disorder. Recall that everything drifts from rare, ordered arrangements toward common, spread out ones, and that this drift is what the second law describes. A measurement runs against that drift in a small and local way. It builds a faithful match between a pattern inside the craft's memory and a condition out in the dark, and a faithful match is a rare, ordered, low-entropy thing. To make it, the craft has to pay the same toll the body pays to stay alive. It creates a pocket of order inside itself and dumps at least as much disorder as waste heat into its surroundings in exchange. Knowing something has an entropy price, and the price is settled in heat pushed out into the cold. Learning is not free of the second law any more than living is. It rides the same current, buying a scrap of local order at the cost of a little more disorder loosed into the world. Physicists found a hard floor beneath this, a smallest possible cost that no cleverness can dodge. Handling information, storing it, erasing it to make room for more, cannot be done without releasing a certain minimum of heat, a floor set by the temperature of the device and the deep laws of thermodynamics themselves. Information is not separate from physics. It is physical, as bound to energy and heat as motion or mass, and a machine that thinks and remembers is a machine that must warm its surroundings to do it. The faint waste heat we watched, leaking from Voyager's electronics, was never only a side effect of running current through wires. Part of it was the unavoidable price of turning the raw conditions of interstellar space into ordered, recorded knowledge. The craft was warm, in part, precisely because it was learning. Then there is the last step, carrying that hard-won knowledge home, and it too is paid in energy. A recorded fact sitting in the craft's memory helps no one until it crosses the gulf back to us. And crossing that gulf means pouring power into radio waves, shaping raw energy into a patterned signal that carries the bits across the dark. The same 20 watts we measured earlier, the strength of a refrigerator bulb flung across the whole width of the solar system, is ordered energy doing ordered work, encoding what the craft learned into a whisper aimed at Earth. Warmth kept the senses alive, warmth kept the memory intact, and warmth, in the form of that faint transmitted power, carried the findings across the emptiness to the only place that would ever care about them. From the first flicker of a measurement to the last radio wave leaving the antenna, every stage of knowing ran on the heat the plutonium made. Step back and the shape of it settles into something plain. For a few decades, a small margin of warmth let a fragment of our own senses reach into a place no living thing could ever survive, feel what was there, and send word back. No human body could last a moment out past the heliopause. No eye could see that faint magnetic weather. No skin could count those thin particles. The craft did it for us. And the only thing that made it possible was keeping a little metal warm enough to work. The heat was for perception. It was the thin, fading currency that bought us a set of eyes and ears in a place we will never go. And it purchased something no amount of later cold can take back. Once a thing is known, once the signal has arrived and the fact is ours, the cooling of the craft cannot unlearn it. The warmth spent itself, but what it bought stays bought. I keep turning over how little of the craft's whole existence this knowing will have taken up. A few decades of warmth and sensing and reporting set against hundreds of millions of years of cold, silent drift still to come. The part of its life where it could feel the universe and tell us about it is the briefest sliver of the time it will exist at all. A short, warm flicker at the very start of an almost endless quiet. The same is true, in its own way, of the plutonium, of the mission, of the whole warm chapter we have been following. It was always going to be short. The cold was always going to be long. The warmth was never the permanent state of things. It was a brief, costly, deliberate exception, held against the dark just long enough to learn something true and then allowed to fade. So if the warm, knowing part of the craft's life is this short, and the cold, silent part is this vast, what does it mean that the same proportion may be written into everything, including the warm, knowing, fading thing that is you, lying here tonight? The proportion is written into you, and into everything that has ever been warm. A brief flare of heat and order against a vast stretch of cold and stillness is not the craft's peculiar fate. It is the basic shape of how anything warm exists at all, anywhere in this universe. To see why, we have to ask a question we have been circling without naming. Why is there any warmth out here to begin with? Why is the cosmos not simply cold all the way through? The answer reaches back to the same law of spreading we followed through the entropy of a cooling cup. Heat flows from hot to cold, always, everywhere, evening itself out toward one uniform temperature. If that were the whole story, the universe would long ago have settled into a single lukewarm sameness, every hot spot drained into every cold one, nothing warmer than anything else. There would be no warm plutonium and no cold space to lose it to, no fire and no dark, just one flat temperature stretching in all directions forever. And in that perfectly even universe, nothing at all could happen. Every engine, every storm, every living cell, every act of thought runs on a difference in temperature, on heat having somewhere colder to flow. Wipe out the differences and you wipe out the possibility of anything changing, anything moving, anything being alive. So the fact that there is warmth here at all, unevenly, in pockets, is the fact that makes everything else possible, and that unevenness has a source we can name. The universe did not begin in the flat, spread-out sameness it is drifting toward. It began concentrated and smooth in one way, but exquisitely primed to clump under gravity, and gravity spent billions of years pulling matter together into dense knots. Squeeze matter tightly enough, and it heats, until deep in the core of a gathering cloud, the pressure lights a fire that holds off the collapse. That is a star. Every star is a pocket of concentrated heat, a local island held far from the cold average, burning because gravity gave the universe somewhere to pile its matter into. The warmth in that spacecraft traces straight back to one of those fires. The plutonium was forged in the death of a star, its heavy atoms built in a furnace that was itself a rare island of heat in the dark. Every warm thing you have ever touched is borrowing, at some remove, from a difference in temperature the universe has not yet finished spending. This is where the whole arc of the craft story becomes the arc of everything. A star, like the spacecraft, is a warm thing losing heat it cannot fully replace. It burns brilliantly for a while, holds off the cold with the fire in its core, and then, its fuel spent, it too cools and fades toward the temperature of the sky. Timescales are vast beyond feeling, billions of years rather than decades, but the shape is identical. A source of order, kindled against the dark, shining while it can, and slowly surrendering its warmth to the cold that surrounds it on every side. The same curve we trace through a fading generator runs through every star that has ever burned, only stretched across spans that make a human life invisible. And the same law that dooms the craft's warmth to fade dooms the stars as well. One by one, across time almost too long to write, they will burn through their fuel and go out, and the great temperature differences that power everything will slowly even away. Physicists have a name for where this leads, if it leads anywhere at all, and it is worth being careful about how firmly we say it. The far future the second law seems to point toward is a universe where every difference has been spent, every fire burned out, every warm thing cooled to the same faint temperature as the dark around it. A cosmos of perfect, uniform cold, with no hot and no cold left to tell apart, no flow of heat anywhere because there is nowhere for heat to flow. In that state nothing can change and nothing can happen, because every source of order has finally been paid out into disorder. It is the ultimate destination of the same drift that cools your coffee and your body and the craft. Whether the universe truly ends that way, we do not know for certain. It rests on assumptions about a cosmos we have only begun to understand, and honest physicists hold it loosely. But within everything we can presently see, the direction is unmistakable. The warmth is a passing thing. The cold is what remains. Set against that immense backdrop, the spacecraft stops looking like a lonely machine dying slowly in the dark and starts looking like exactly what it is. It is a small, ordinary instance of the most universal process there is. A pocket of warmth and order, kindled deliberately, holding itself against the cold for a little while, spending its heat to do something no cold thing could do, and then letting that warmth go the only way warmth ever goes. It is not failing. It is not tragic. It is doing precisely what a star does, what a body does, what every warm thing in the universe has always done, only on a scale small enough and near enough in time that we can watch the whole of it. The craft is a lesson in miniature about the single deepest tendency of everything that exists, played out slowly enough for a human being to follow from start to finish. And that is what makes it feel less like an ending and more like a companion, lying here in the dark thinking it through. You and the craft and the stars are all the same kind of thing, briefly warm in a cooling universe, made possible by a difference in temperature that will not last forever, spending that difference while it lasts on motion and knowing and being alive. The warmth was never meant to be permanent. In you, in the craft, in the sun overhead, it is a passing gift drawn from an unevenness the cosmos is slowly using up. So, if the warmth is always temporary, and the cold is always waiting. What is the right way to hold a thing that is warm right now, tonight, knowing exactly what it is and exactly how long it lasts? There is a way to hold a warm thing that comes only from understanding what warmth actually is, and it starts with a fact that sounds almost contradictory. The energy in the universe never runs out. It cannot. Energy is perfectly conserved, never created, and never destroyed. The same total quantity now as at the beginning of everything. So, when we say the craft's warmth is running down, we are not saying its energy is vanishing. Every bit of heat that leaves the plutonium is still out there, spread into the metal, spread into space, conserved down to the last trace. Nothing is lost. And yet the warmth still fades, the craft still cools, the mission still ends. So what exactly is running out, if not the energy itself? What runs out is not the energy, but its usefulness. And the difference between those two is one of the most quietly profound ideas in all of physics. Energy can do work for us only when it is concentrated. Only when there is a difference to exploit. A hot place beside a cold one. The heat locked in the warm plutonium is useful precisely because the space around it is cold. That difference is what lets it flow. And a flow is what turns a wheel, lights a signal, keeps an instrument alive. Once that same energy has spread out evenly, once the warm and the cold have blended to one temperature, the energy is all still there, every last unit of it, but it can no longer do anything at all. It has become useless while remaining fully present. This is the real currency the craft has been spending. Not energy, which is conserved, but the concentration of energy, the difference, the usefulness. Every joule the craft ever spent is still in the universe. It simply cannot be gathered and used again. This gives the whole story its true and final shape, sharper than the word cooling ever caught. The craft was handed a fixed dowry of usefulness the day the plutonium was sealed, a certain amount of concentrated, spendable warmth, and from that day it could only spend it down. Not because it was leaking energy into nowhere, but because concentrated energy, once used, spreads into the useless even sameness the second law drives everything toward. The mission has always been a slow conversion of useful heat into useless heat, of difference into blandness, of a warm ordered gift into the spread-out disorder that is the universe's one certain direction. That conversion runs one way and cannot be undone, and it is the same one-way road we found underneath time itself. To spend usefulness is to move forward in time. There is no way to do the one without the other. If usefulness only exists as a difference, and if every difference is temporary, then the value of a warm thing was never in its lasting. A warmth that lasted forever, that never spread and never faded, would be a warmth in perfect balance with everything around it. And a thing in perfect balance can do nothing. It cannot flow, cannot work, cannot power a single measurement or a single heartbeat. The very fact that the craft's warmth is spendable, that it drains away as it is used, is inseparable from the fact that it could do anything at all. Its warmth mattered because it was temporary. A permanent warmth would have been a dead one. The fading was never the flaw in the gift. The fading was the gift working, spending itself down in the only way that useful things can ever be spent. So the honest way to hold the craft is not as something being slowly robbed of its heat by an indifferent cold. It is as something spending a real and finite gift exactly as it was meant to be spent, on knowing, on reaching, on doing the work that only concentrated warmth can do. The cooling is not a theft. It is the gift being used. Every degree the craft has lost across almost 50 years went into holding an instrument alive one more day, into carrying one more finding home, into keeping a small ordered voice, speaking from a place too cold and too empty for anything else we know to survive. The warmth did not drain away for nothing. It drained away into everything the craft accomplished, and that spending was the whole point of ever having it. A warm thing is a gift you can only keep by using, and the craft used it well. Lie here and feel your own warmth leaving you, softly, into the room, and it is the same truth in a smaller frame. The heat draining off your skin tonight is not being stolen. It is the visible edge of everything alive inside you, the byproduct of a body spending its own concentrated energy on the work of being here, awake, thinking, breathing, warm. You cannot hold that warmth still any more than the craft can. The moment it stopped flowing out of you, the moment your temperature matched the room exactly and settled into perfect balance, would be the moment nothing in you was working anymore. Your warmth leaves because you are alive. The leaving and the living are the same event, seen from two sides. And so the fading of a warm thing, in the craft and in you, is not the sad part of the story. It is the whole of what it means to be warm at all. So what is left to understand, once we see that the warmth was always meant to be spent, and that the spending was never loss but use? There is a limit on what we can ever know about the craft, and it has nothing to do with the faintness of its signal or the age of its parts. It is deeper than that, built into the structure of the universe itself, and it means that the Voyager 2 we speak of tonight is, in a strict and unavoidable sense, a thing we can never actually reach. The warmth we have been tracking, the temperature we picture holding steady out there right now, is not something we have access to. We are always, only, in touch with its past. The reason is the same finite speed we met when we followed the signal home. Nothing carries information faster than light, and light, for all its speed, still takes time to cross real distance. The craft is now so far away that its signal, moving at the ultimate speed, needs close to a full day to reach us. When we listen tonight and hear that faint tone confirming the craft is warm and alive, we are not hearing how it is. We are hearing how it was, most of a day ago, when that signal first left the antenna. In the hours since, anything could have happened out there, and no word of it can possibly have arrived. The craft we are in contact with is always a memory, a report from the recent past, sealed and sent before we could know its contents. The present state of Voyager 2, its temperature at this exact instant, is a fact the universe simply does not let us hold. This is not a failure of our instruments that a better antenna could fix. It is a wall written into the nature of space and time. Every fact about a distant object has to travel to us to be known, and that travel takes time. So every distant thing we observe is shown to us as it was when the light left it, never as it is. Look at the sun and you see it as it was 8 minutes ago. Look at the next star over and you see years into its past. The farther out you look, the deeper into history you are peering, until at the edge of the visible universe you are seeing light that left its source before the Earth existed. We do not see the cosmos. We see its past, layered by distance, each object showing us an older and older version of itself the farther away it sits. Voyager 2 is close by those standards, its past only a day stale. The principle is identical. We are never in contact with the now of a distant thing. We are in contact with its echo. The strangeness runs deeper still once we ask what the now of a distant object even means, because relativity took that word and complicated it in a way we are still not fully at peace with. For things sitting close together and moving slowly, we can agree easily on what is happening at the same moment. Stretch across the enormous gulf out to the craft, and that shared present quietly loses its footing. Two observers moving differently can disagree about which distant events happen at the same time, and neither of them is wrong. The universe does not hand us a single master clock ticking the same instant everywhere at once. The idea of what Voyager 2 is doing right now, at this precise shared moment, is not just hard to observe from here. It may not be a fully defined thing at all. The present, out across that distance, is a fuzzier notion than our daily lives ever let us suspect. So when we say the craft is warm tonight, We are making a quiet leap we rarely notice. We are trusting that the physics we understand kept running the same way in the hours since the last signal left, that the plutonium went on decaying, that the metal went on holding its heat, that the curve we have drawn continued smoothly through the gap we cannot see. Almost certainly it did. The laws that govern that warmth are among the steadiest we know, and there is no reason to expect them to have faltered in the last day. But the certainty we feel is a certainty about the past extended forward by trust, not a certainty about the present confirmed by sight. We believe the craft is warm now. We know only that it was warm then. Every living connection we have to that machine is a thread reaching backward in time, and the present moment of it stays forever just out of reach, hidden behind the time its light still needs to cross the dark. Sit with how far this reaches. It is true of everything you have ever perceived. The light reaching your eyes from across the room left those surfaces a tiny fraction of a second ago. The warmth you feel from your own hand, the sound of your own breath, each reaches your awareness after a small delay, while the signal travels and your body processes it. You are never quite in the present either. You live, always, a sliver of a moment behind the world, assembling a now out of information that is already, by the time you hold it, the past. With the craft, the delay is a day. With the room, it is a flicker. With your own body, it is the briefest instant. The gap shrinks toward nothing as things come closer, but it never quite closes, and the present you feel yourself living in is always a reconstruction, built a heartbeat, late from signals already on their way to becoming memory. The craft, then, is not as strange as it first seemed. It is only a clearer, slower version of the condition we all live inside. Warm in a past we can confirm, uncertain in a present we cannot see, known only through echoes that take time to arrive. We reach toward it across the dark the way we reach toward everything, a little behind, holding a report and trusting the world stayed lawful in the gap. And the warmth we are trusting to still be there, most of a day away, is real, or was real, when its light set out toward us. That may be as much presence as the universe ever grants to anything at a distance. So if even the now of a warm thing is always just beyond our reach, held one delay away behind the speed of its own light, what is actually left for us to hold of it, here, tonight? What we hold of the craft was never the craft itself. We have never touched it, never seen it with any eye, never stood in its cold to feel whether it is warm. What we hold is something thinner and stranger, and once we name it clearly, it changes what the whole mission has been. What we hold is a pattern, a steady stream of information that the craft shaped and sent, and that we caught and kept. The metal is 14 billion miles away and always was. What crossed the gap to us was never matter at all. It was form, structure, the arrangement of a signal, and that is a different kind of thing entirely. Follow what actually travels from the craft to you, and the point sharpens. No physical piece of Voyager 2 ever arrives here. The radio wave that reaches our antennas carries no substance from the craft, not a single atom of it. What it carries is a pattern impressed upon it, a rise and fall shaped to stand for the numbers the craft measured, the way the grooves in an old record carry music without containing any sound of their own. The wave is just the messenger. The meaning rides in its shape, in the precise sequence of its variations, and that shape can be copied into our computers, written down, stored, and shared without any of the original wave remaining. The thing of value was never the energy of the signal, which scatters and fades. It was the arrangement that energy carried, and an arrangement can be preserved perfectly even as every physical trace of its arrival disappears. This is a genuinely different way for a thing to exist, and physics has come to take it seriously in its own right. A pattern is not tied to any one lump of matter. The same arrangement of information can live in a radio wave, then in a magnetic trace on a disk, then in the firing of the cells in your memory, passing from one physical home to another while remaining, as a pattern, the very same thing. The craft's measurement of a magnetic field out past the edge of the sun's reach existed first as a real condition in space, then as a state inside an instrument, then as a signal in flight, then as a record here, then as an understanding in a human mind. At every step, the matter changed completely. The pattern held. What Voyager sent us was not stuff. It was structure. And structure can outlive every particular thing that ever carries it. The craft will cool and erode to nothing across the ages, and the patterns it sent home can remain intact the entire time, held in copies it will never know about, untouched by anything happening to the cold metal that first gave them shape. This lifts a strange kind of permanence out of a story that has been about fading from the start. The warmth fades. The signal fades. The metal itself will slowly wear away, but the information the warmth was spent to gather does not obey that same decay. Once a pattern is faithfully copied, it can be copied again, endlessly, with no loss, each copy as complete as the first. A measurement understood and recorded here is no longer at the mercy of the craft that made it. It has stepped free of its origin, and it can persist through copy after copy long after the original sensor has gone cold and silent and eventually to dust. The heat was temporary. The metal is temporary. The pattern the heat purchased is, in a way nothing physical ever quite manages, able to be kept. This is the one thread in the whole story that does not have to fade with the warmth that first produced it. There is a limit on this, and honesty requires marking it plainly rather than letting the idea float free of its cost. A pattern can only persist if something keeps carrying it, if some physical thing holds it and some further physical thing copies it forward before the first wears out. Information is not magic and not weightless. It always lives in matter, always needs a physical home. And if every copy of a pattern is destroyed, the pattern is gone as surely as any burned page. The permanence is real but conditional. It lasts only as long as the chain of carriers lasts, only as long as something goes on holding the shape and passing it along. What the craft achieved was to get its patterns across the gap and into a place, our world, where that chain of carriers is rich and self-renewing, where a finding can be copied and recopied across minds and machines faster than any single carrier decays. It handed its knowledge to a system that can keep a pattern alive. That was the deepest thing the warmth ever bought. Not a measurement, but a measurement lodged somewhere it can outlast the instrument that made it. Bring this back to the body lying here, because you are the same kind of thing, more than you might expect. Almost every atom in you now is not the atom that was here years ago. Your body swaps out its material constantly, cell by cell, molecule by molecule, rebuilding itself from the food and air passing through. The stuff of you flows and is replaced. What stays is the pattern, the arrangement, the particular structure that keeps being copied forward onto new matter as the old matter leaves. You are not the atoms. You are the shape the atoms are held in, a pattern persisting across a body that is always physically exchanging itself for a fresh one. In that plain sense, you are far more like the signal than like the craft. You are not the metal. You are the message, carried forward on matter that comes and goes, held in a form that lasts longer than any single particle composing it. The same distinction that let the craft's knowledge outlive its cold body is the distinction that lets you remain yourself across a lifetime of atoms arriving and departing. So the fading we started so worried about turns out to leave one thing untouched, in the craft and in you alike. The warmth goes. The particular matter goes. The pattern, if something keeps carrying it, can go on. The craft spent its heat to lodge a set of patterns safely in the one place able to keep them, and you spend your warmth, night after night, to hold your own pattern steady on a body forever trading itself away beneath you. Both of you are structures riding on matter that will not stay, keeping a shape alive against the drift that pulls everything apart. And if what lasts of a warm thing is never the warmth or the matter, but only the pattern it manages to pass on, then a last question waits underneath all of it. What pattern is a single quiet spacecraft, cooling at the edge of everything, actually leaving behind? The pattern the craft leaves behind is not only the signals it sent, it is the craft itself. The object drifting out there is, in the most literal physical sense, a message. And it says something the moment anything ever finds it, without a single word being read. What it says is that the matter it is made of was arranged, deliberately, against everything the universe normally does to matter left alone. A lump of ore does not become a shaped antenna by chance. The very existence of that ordered thing, out among the random dust, is information written in structure rather than in language. To feel why that counts as a message, we have to return one last time to the law of spreading and disorder. Left to itself, matter drifts toward the common jumbled arrangements, toward rock and dust and gas with no particular order to them. The overwhelming majority of ways to arrange a pile of atoms produce something formless, because formless states vastly outnumber ordered ones. A precisely machined object, with its parts fitted and its metals refined and its shapes cut to purpose, is one of the staggeringly rare arrangements, a configuration so unlikely that random processes will effectively never stumble into it. That improbability is exactly what makes it recognizable. Anything encountering Voyager 2 and seeing that impossible degree of order would know at once that it did not form on its own. Chance does not carve smooth curves and fold thin foil and etch fine grooves. Only something that gathered energy and spent it on ordering matter can push against the drift that hard. The craft is a frozen act of order, and order at that level is a signature. This is the same principle that lets us tell a tool from a stone the moment we pick it up. A rounded pebble could be the work of a river, tumbled smooth by chance over ages. A blade with a deliberate edge could not. The difference we feel instantly is a difference in improbability, in how far the object sits from what random forces produce on their own. A made thing carries the mark of having been ordered on purpose, and that mark is legible to anyone who understands that matter does not organize itself this way without something spending energy to make it so. Voyager 2 carries that mark on the largest and clearest scale, a whole intricate machine of refined and fitted parts, unmistakably the product of something that understood its materials and shaped them with intent. Every curve of it is a sentence in a language that needs no translation, saying only this: something here knew how to do this. And the deepest layer of the message is not in the shape of the metal, but in what the shape implies about its makers. To build a craft that can survive interstellar cold, hold its heat for decades, and speak across the width of the solar system, you have to understand the very laws we have been tracing all along. The object is a working proof that whoever made it had grasped how heat moves, how radiation carries energy across emptiness, how the atom can be persuaded to give up its warmth, how a faint signal can be shaped to cross an impossible gap. The craft is not only ordered matter, it is ordered matter that could only have been made by minds that had learned the physics of their universe. Its existence certifies that somewhere, briefly, a part of the cosmos came to understand the rules the cosmos runs on. That is a strange and profound thing for a piece of drifting metal to prove. The universe produced, in us, a small region of itself that figured out how it works, and then flung a token of that understanding out into the dark to carry the fact onward. The craft is not eternal, and its message is not guaranteed to be read. The odds that anything will ever encounter it are almost impossibly small, given how empty the space it travels truly is, how thinly the stars are scattered, how vast the gaps between them run. Most likely it will drift for its hundreds of millions of years and be seen by no one, its ordered structure slowly worn back down toward the formlessness everything eventually returns to. The message is real, but it is a message in a bottle cast into an ocean so large that the bottle will probably never wash ashore. What matters is not the likelihood of it being found. What matters is that the pattern was made at all, and sent, and that for a while it exists, carrying its improbable order farther from home than anything we have ever made. You are, right now, one of those staggeringly rare arrangements of matter, a configuration so ordered that no random process could ever have produced it, held far from the formless average by the constant work of staying alive. Every living body is a made thing in exactly the sense the craft is, a pocket of deep improbability sustained against the drift toward disorder, its atoms arranged with a precision that chance could never reach. And like the craft, you spend energy without pause to hold that order in place, warming the world around you as the price of remaining, for now, this particular impossible shape. The difference is only that the craft holds its order frozen and passive, while you renew yours actively, moment by moment, breath by breath. Both of you are the universe arranged, briefly, into something it does not usually make. Both of you are order borrowed against the dark, kept alive only as long as the warmth lasts to maintain it. So the whole long story folds down to a single quiet shape, and it belongs as much to you as to the machine. A rare pocket of warmth and order, kindled against a cold that vastly outweighs it, spending its heat to know something and to be something for a little while, and leaving behind whatever pattern it managed to press into the world before the warmth ran out. The craft did this at the edge of the solar system, in metal, across decades. You are doing it here, in flesh, across a single quiet night. The physics underneath does not distinguish between you. The same laws, the same warmth, the same slow and honorable spending of order into the dark. And now that we have found, what does it change? To lie here tonight and know that you are made of the very same fading, borrowed, deliberate warmth as a spacecraft cooling at the edge of everything. It changes almost nothing, and that is the gentlest part. The warmth leaving your body tonight was always going to leave, the same way it leaves the craft, the same way it leaves the stars. Knowing the physics of it does not add a single worry that was not already true. It only lets you see clearly what was happening all along. You are a warm thing in a cooling world, holding your heat for a while, spending it on being alive, letting it go a little as the night comes on. None of that is new. You have done it every night you have ever slept. Tonight you simply understand what you are doing. Feel where your warmth is going right now, off your skin as that faint infrared glow, into the sheets by touch, into the air rising slowly around you. It is leaving by every door we followed all the way out to the edge of the solar system, and it is being remade inside you just as steadily, from the quiet fire of the day's food burning low in your cells. The balance you have kept without a thought your whole life is the same balance the craft has kept for 50 years. Warmth arriving, warmth leaving, a temperature held in the space between. You have never once had to manage it. Your body has simply done it, faithfully, through every night you can remember and every night you cannot. There is something steadying in that. The thing keeping you warm asks nothing of you at all. As sleep comes, you let a little of that warmth go on purpose. Your body eases its own temperature down by a fraction of a degree, softening the inner fire, letting the heat drift out into the cool of the room. The cooling is not something happening to you against your will. It is part of how you fall asleep at all, woven into the signal that tells you the day is finished and it is safe to let go. The same slow loss of heat that carries a spacecraft toward the cold is, in you, tonight, the quiet mechanism of rest. You are cooling, gently, the way everything warm eventually cools, and in your case the cooling is the doorway into sleep. You do not have to hold on to the warmth. Letting it go a little is exactly what lets you rest. Far out past everything, the craft is doing the same thing you are, only slower, holding its heat against the cold, spending it on staying alive, letting it fade by a curve neither of us can reverse. It has been warm out there the entire time you are listening tonight, and it will still be warm when you wake, and warm for years of nights after this one, quietly making heat from unraveling atoms in a place too cold and too empty for anything else we know to survive. It is not lonely, and it is not suffering. It is simply warm, for now, the way you are warm, for now. Two small ordered things holding their heat in a universe that is slowly, patiently, cooling all the way down. There is a kind of company in that, across all that distance. The same physics runs through both of you. The same warmth. The same slow and honest letting go. So let the warmth leave tonight without holding it. That is what warmth is for. It was never meant to be kept forever, in you, or in the craft, or in the stars that made the atoms in your hand. It was meant to be spent on knowing something true, on being alive for a while, on one more quiet night of understanding a little more about the world before letting the day dissolve into rest. You spent yours well today, simply by being here, curious and awake in the dark. Now the fire can burn low. Now the heat can drift out into the room. Now you can let the temperature ease down the way it always does, the way the whole universe does, gently and without any effort of yours at all. The warmth will still be there in the morning, remade from tomorrow's light. It always is. Thank you for spending this quiet stretch of the night out here, following the warmth all the way to the edge of everything and back to your own steady heat beneath the blanket. There is nothing left to understand tonight, and nothing left to hold. The craft is warm, far away in the dark. You are warm, here, right now. And the slow letting go of that warmth is not an ending at all. It is only rest. Let it come. Let the heat drift. Let the day cool into sleep. Sleep well.